Here we have a rational function, x squared plus 1 over x squared minus 9. And so we're going to have to apply the quotient rule when we take the derivative. So let's go ahead and get started with that. We start with the bottom, x squared minus 9 times the derivative of the top, which is 2x, minus the top, x squared plus 1, times the derivative of the bottom. And that's going to be divided by the bottom squared. Now, I do want to simplify a little bit because I'm going to have to take the derivative again. So I will go ahead and factor out a 2x in the top, and that's going to leave x squared minus 9. And now distributing the minus sign across the parentheses, we have minus x squared minus 1 over x squared minus 9 squared. Now the x squareds are going to cancel, and that leaves us with 2x times negative 10 over x squared minus 9 squared, and that is negative 20x divided by x squared minus 9 squared. Now recall that the critical numbers for f prime are going to be the values for which the function is equal to 0 or does not exist. And so that means that setting the numerator equal to 0, we get x equals 0. And setting the denominator equal to 0, we get x equals plus or minus 3. And so we have three different critical values for f prime, and we will go ahead and create a sign chart. So we'll mark off our critical values on a number line, and we also want to pick some test values or test numbers on each of the intervals that are created by these critical values. So negative 4, negative 1, positive 1, and positive 4. Now all we have to do is take this function, our first derivative, put it in your graphing calculator, and then just substitute each of these 4 test values and determine what the sign is of your solution. And so substituting in negative 4, we get a positive value for f prime. Substituting negative 1 in, we get a positive value again, so there's no sign change. But plugging in 1, we get a negative, and plugging in 4, we also get a negative. Now, what does that mean for us in terms of the original function, f of x? Well, it means that on the interval from negative infinity to negative 3, f of x is increasing. And then we have an asymptote, a vertical asymptote, and then the function continues to increase. Then, between 0 and 3, the function is decreasing, and we have a vertical asymptote that interrupts our function, but it continues to decrease on the last interval from 4 to infinity. Now, I notice that my function changes from increasing to decreasing, and so what that tells me is that we have a max located at x equals 0. Now, let's talk about concavity, and let's look at the second derivative. So the second derivative is the same as the first derivative of the first derivative. So I can take this function and differentiate it again using the quotient rule. So we have the bottom, x squared minus 9 squared, times the top, negative 20x, minus negative 20x. And so we have the bottom, x squared minus 9 quantity squared, times the derivative of the top, which is negative 20, minus the top, negative 20x, times the derivative of the bottom, which we apply the power rule and the chain rule. We have 2 x squared minus 9 times the derivative of the inside, which is 2x, all over x squared minus 9 to the fourth power. Now I'm going to go ahead and factor out an x squared minus 9 on top, and that leaves us with an x squared minus 9 in the first term times a negative 20. And let's go ahead and distribute the minus sign. So minus a negative 20 gives us positive 20x times 2 is positive 40x times 2x is positive 80x squared. And let's just simplify again. So we can cancel out an x squared minus 9, and that'll leave us with an exponent of 3. And in the top, we now have negative 20x squared distributing plus 180 plus 80x squared over x squared minus 9 to the third power, and this gives us, combining like terms, 60x squared plus 180 over x squared minus 9 cubed. And I think to find critical values, it might help to simplify. Let's pull a 60 out. We have 60 times x squared plus 3 over x squared minus 9 cubed. And if you take the numerator and set it equal to 0, there's no real number x that will allow that to be equal to 0. So this only has imaginary roots. And so what that means for us is that there's going to be no point of inflection. And we'll give a reason for that, because 60 times x squared plus 3 is not equal to 0 for any real number x. And so our only critical numbers in this case are going to be plus or minus 3 from the denominator, where this function is also undefined. Now I've got so much going on here, I am going to draw a box around this just so I can find it easily, because we're going to have to substitute values in a moment. So let's go ahead and let's put our critical values on the number line. Now let's pick some test values that are on each of these three intervals. So maybe -4, 0 would be a great one for the middle, and +4. And we'll put this function in the graphing calculator, and we will just simply substitute our test values one at a time and see what is the sign of f double prime of x whenever we evaluate those numbers. And so we get a positive value when we substitute -4 into the second derivative. We get a negative value when we plug in 0, and we get a positive value again when we substitute 4. Now, what does this tell us about f of x? Well, since f double prime is positive, on this interval, the function is concave up. Since it's negative between -3 and 3, it's concave down, and since it's positive from 3 to infinity, it's concave up. So we've got a lot of information now. Maybe we can graph our function. All right, so here's what the function looks like, but let's give some information. So let's talk first of all about the domain. So what is the domain of this function? And I'm not going to get it from the graph, I'm going to get it from our work. So let's go back and take a look. So the domain is determined by our critical values for the original function. So notice that we have x squared minus 9 in the denominator, so we have vertical asymptotes at x equals -3 and +3. And so those are the only values that will be excluded from the domain of our function. So we have three intervals: -∞ to -3, union, -3 to 3, union, 3 to infinity, range. So let's take a look at the range. So the range of this function is going to start out being all real numbers, but we have to consider, do we have any horizontal asymptotes or slant asymptotes? And actually we do. If you look at the ratio of the two leading terms, they're both the same, x squared over x squared. So remember that the ratio of, if they have the same degree, the ratio of the lead terms will give you a horizontal asymptote. So we have a horizontal asymptote at y equals 1, and for that reason, the value 1 is going to be excluded. So we can also see that we have a horizontal asymptote. If you look at the lead coefficients, they have the same degree. And so if you take the ratio of the coefficients, we have 1 over 1. So we have a horizontal asymptote at y equals 1. Looking at our graph, we can see that the function does not cross the horizontal asymptote. And so for that reason, we will exclude 1 from the range of our function. So negative infinity to 1, union 1 to infinity. Notice the parentheses indicating that we're not including these values. Finally, let's talk about those asymptotes. Okay, so we do have a horizontal asymptote located at y equals 1, and we have vertical asymptotes located at x equals 3 and x equals negative 3. Now let's talk about the results of our first derivative and second derivative test. So where is the function increasing? So the function is increasing from negative infinity to negative 3, and again from negative 3 to 0. It is decreasing from 0 to 3, and again from 3 to infinity. Now its concavity is going to be up from 0 to negative 3 and from 3 to infinity. So concave up from negative infinity to negative 3, union 3 to infinity, and it is concave down between negative 3 and so this combined with a graph, well, first of all, this information can help us sketch a curve like this. Now remember, when we're sketching curves, we're not necessarily concerned about creating a t-table and plotting the points. We're concerned about the overall behavior of the function, this information here. And so sketching a curve is different than graphing. So here we've got a graph, but we could see how we could sketch something kind of like this based on this information. And that's kind of leads us into the next few examples where we're going to try to do this. Instead of creating an exact graph of a function, we're going to do this type of analysis, and then we're going to see if we can sketch a curve that will fit these characteristics.